All right. Welcome everyone to Acid Base Chemistry Day 2. Uh, so acid base chemistry, I keep saying this, um, but I'll reiterate it over and over again. This stuff gets pretty tough, and I know some of you guys struggled to finish the last exam, and I know things are hard right now because it's a pandemic and you're having to learn from home. Um, and you're young and uh, I don't know, there's a lot of stuff that's probably way more interesting than chemistry right now, and I get that. um, Even as a professional chemist, I feel that in my own life sometimes. So uh, but um, yeah, if you struggle to finish the last exam because you felt like there wasn't enough time, I implore you to just practice more problems. um, that exam would have been a normal exam that we'd have given. Well, I don't want to say this in a way that feels insulting if you did poorly on the exam, but that exam would have been a normal exam, but probably a little bit easier than one we would have given in class during the normal semester. It wasn't as calculation heavy. There was maybe one problem on there. That one problem about the mystery salt was kind of hard, but outside of that, a lot of those problems were pretty straightforward. So if you found yourself struggling on it, um, my recommendation would be to work more problems. I mean, that's always my recommendation, uh, but yeah, you just got to get more familiar with the material. It should take a couple of minutes to work through those problems. Um, some of the harder ones, if you have to think about it or something, yeah, those might take a little bit more time. Uh, but yeah, the acid base stuff is particularly calculation heavy. Um, and you're going to definitely want to go into the exam kind of knowing how to solve most problems straight up. Like, I know it's open book, so there's this feeling of like I can go on the internet and I can kind of find other resources or find similar problems and work it as I go. But you're going to run into time crunch problems pretty quickly if you do it that way. So just heed that advice of staying on top of your work here. Usually the average for so normally our average is historically for the regular exams for every exam, let's say this semester, with the exception of the acid base ones in the 70s, like mid 70s to low 70s. And then the acid base exam is usually like a 60 or below. So students really struggle on this stuff. Um, that being said, um, even though it's a lot of work to learn this stuff is some of the cooler stuff that I think we learn in the course. This is my favorite chapter or unit or set of chapters, or however you want to think about it, in the whole 302, 301 series. Uh, Acid-base chemistry is super, super important for everything. Like if you want to understand how life works or biology works, or like why the oceans, why climate change is causing the oceans to become more acidic. Acid-base chemistry sort of ties into all of that. Yeah. So your grade for the first test, whatever, did it not spit out your grade when you were done taking the exam? That's your grade. Uh, I'm going back. Okay, so that's your grade. There's no curve on the first exam. I talked to Simolenko a little bit about that. Um, Even if we did curve it, it would only be for a couple of points, and it's not going to be super impactful. So if we do, it shouldn't be super impactful on your grade in the short term. As in, for people who are making decisions about dropping the course, it shouldn't have affected that. If we do put a curve in, we'll do a curve at the end of the semester, and that helps. I think that's beneficial for everybody. I talked a little bit about this in my office hours. I think that's beneficial for everybody because um, you get one drop exam. So if your drop exam is, uh, if you're like, if we curve one of the exams and you drop that exam, then you don't benefit from it. Whereas if we just curve all the grades at the end, um, then everybody kind of benefits. It also gets rid of like curving the exams if like students just aren't even taking the exam because they're going to drop the course. It kind of screws with our ability to kind of properly set grades. So anyway, I need to go in and put your grades up and fix them. I'm just dragging my feet on that because it's like a manual data entry job, and our TA did, he's already doing a lot of work, so I'd feel like a jerk kind of getting him to go in and fix it. So I have to go fix it, but I have to find time to do that. So I appreciate y'all's patience on that. All right. If we don't drop the exam, can we exempt the final? Currently, everyone must take the final. So plan on taking the final. If for some reason, I'll talk to Samoilenko at the end of the session, and we can discuss whether or not we do that. Typically, we don't give an exemption on the final, but it is true if you don't drop an exam, it feels good. Anyway, all right, let's talk about that at the end of the semester. How about that? Right now, the syllabus is a kind of our Bible. Just assume that everything in the syllabus is, the syllabus is kind of like the worst case scenario. You know, like it's like we don't curve the grades, we don't curve the grades, you absolutely have to take the final, et cetera, all this kind of stuff. But we sometimes at the end will change things, but if we do change them, it's almost always in the favor of you guys. We never change it to make things worse. We're not going to, for example, change the grading scale to where, you know, I don't know, more people are failing, or the A becomes more difficult to get, like a 99 and up is an A or something, nothing like that. All right. So let's talk about acid-base chemistry, because there's lots and lots of stuff to talk about here. So yeah, I was making notes before class, just looking over it, and it's that there's actually, like, it's not that much stuff. It's just very confusing, I think. The stuff that you do have to learn, and like how to put it all together, I think, is where students sort of get challenged. So let's work through some of that stuff, and then I've made some notes for myself about like what types of problems to make, both for our exam and for you guys to practice on. So I'll try and get some problem videos up before the end of the week, so you can kind of get on practicing this stuff. I know we have a lot of problems, but it's sort of like there's just a lot of problems, and it's sort of, there's 100 problems on there, and they're sort of all mixed up. So that's not the best in terms of just pacing for the course. It's not the best thing. All right, so let's start with the fundamental type stuff here. So I'm trying to remember what I talked about last week. Let me look at my notes from yesterday or Monday. Okay, yeah, we spoke a little bit about, we just did definitions. Yeah, so we've got, hopefully in your high school course, and this depends on where you went to high school at and whether or not it was like a fancy high school where you had like a guy with a PhD teaching you chemistry who won a Nobel Prize, or you had like Coach Bob who took, you know, chemistry and like just, or maybe didn't even take chemistry and just like that, they just slotted him in to teach your course. I know that kind of affects kind of how you come into this course. So if you had Coach Bob, I'm sorry. If you had a really fancy thing, then some of this stuff might be review for you. Either way, we'll get you on the right path here. All right, so acid-base chemistry, we're almost, in this course especially, we're almost always talking about being in water. So water is typically our solvent. You can talk about acid-base chemistry pretty much anywhere. You know, you could talk about acid-base chemistry in the gas phase, for example, or in a different solvent like ethanol or chloroform or something. Yeah, so we're switching up. So there's no lectures on YouTube. We'll do lecture in normal class time, and I'll do YouTube videos on how to solve problems. I keep getting distracted. This is the last thing I'll say about, before I get into the acid-base stuff. So like research shows, if you look in the education like literature on how to teach students, research shows that flipped classrooms where you know, the students kind of do work before they come into class, and then you work on problem solving and all this stuff in class. Students learn better that way. But anecdotally speaking, every single student I've ever talked to in my entire, and I wasn't intentionally trying to run the class, but that's kind of how it started out. But anecdotally, just speaking to students generally hate flipped classes. So practically, I don't think they learn as well. I also wonder if part of it is just a function of being at such a large school. If a flipped classroom doesn't work as well when you have, you know, 200 students in a classroom. You know, if we had a classroom of 10 students where it's like, oh, okay, everybody breaks off and it's like kind of an open dialogue and stuff, maybe it works better for that. But at scale, I found they don't work. So we'll do lectures here and we'll do problem solving on YouTube. So this will be more like a traditional class. All right. So for real this time, acid-base stuff. I'm going to minimize the chat window so I don't keep looking at it. Can't help but answer questions when people ask them. Okay. All right. So water is typically our solvent. You can do the acid-base chemistry anywhere. You know, like if I take their HCl, for example, is a gas, you can get HCl into the gas phase, and it's still going to work like an acid. If I put my hand in a stream of HCl gas or something, it's still going to melt my hand, just like it does in water. So pH is sort of this thing that exists everywhere, but water is our primary place that we look at it. And the reason is that that is obviously the most common solvent on the entire planet. Like 70% of our planet is covered in it. We are essentially like just bags of water, or I forget the exact percentage, but like 90% of our bodies are water. So water is super, super important. And the pH is super important, especially for life, because we only really exist within a very narrow pH range. You know, your blood is buffered at 7.4. If it gets too high or too low, you're pretty much dead. Same thing is true for the ocean. If the ocean gets super acidic, you know, all these different types of organisms in the ocean start dying. Part of that is what we're seeing with the coral reefs. As carbon dioxide concentrations go higher, some of it dissolves in the ocean and makes it more acidic. It turns into carbonic acid. And coral reefs, we can probably find a problem on that. Coral reef is made of carbonate, calcium carbonate, and that's more soluble at low pHs. So that's why those are dissolving. So acid-base chemistry kind of has tendrils into all sorts of different things. We're going to kind of learn the machinery for how to look at acid-base chemistry and how to do these calculations. So, you know, there is a bigger picture, I think, for acid-base chemistry where it is really useful and it is really interesting. Sometimes learning the machinery of how things works is not as cool, right? Like kind of like if for those of you guys who are going on to be medical doctors or engineers, it's like, man, in the big picture, it's really cool to build a international space station or to go and do neurosurgery or something like that. But like learning about that and sort of getting down to the fundamental aspects of it it can be kind of laborious, right? Like you don't just start out building the International Space Station. There's all this other calculations and crap that goes into it. So, but try to stay focused on the big picture and that this stuff is important, especially for those of you who are going into some of the squishier sciences like biology or biochemistry, or even for those of you who are the handful of people probably who are chemistry majors. Okay. And we use it if you go on to take organic chemistry with me. What are we in the fall? In the spring, which hopefully they let me teach. Sometimes they change it at the last minute. We'll do a lot of acid-base stuff in there. I really like that stuff, and it is super important in organic. Okay, all right. So water is typically the solvent. Hopefully I've convinced you that acid-base chemistry is worth learning. Let's take a look at some of the mechanics behind it. So what we're concerned with in acid-base chemistry is the concentration of H+. And in water, H+ doesn't exist as just a free-floating proton. It's almost always bound to a solvent molecule. So we'll write it as H3O+, which is really just water with a proton attached to it, right? So these things are exactly equal. And then sometimes you'll see us just write H+. I'm going to write it as an equal sign. You'll see us write H+. So in water, all of these things are the same thing. And you'll see them used interchangeably in the literature or in different textbooks. And I'll try and be consistent, but you might see me slip up here and there and write them out differently. But generally speaking, if you have H+ in water, it's as you write it as H3O+. Yeah, so I don't know, just a little bit more on that because I feel like we get so deep in the quantitative stuff. So if you imagine water and you're trying to think about acid inside of water, and I don't know exactly how I would ask this on a test, but just this is a good way to like think about what's going on there. So in water, you have like like if you think of a glass of water or something, you've got tons and tons of water molecules in there. And if you put a drop of acid in there, you have a relatively low concentration of H plus. So if I put a drop of acid in there, I have a relatively low concentration of H plus. And so let's say for in this case that I've drawn here, you've got one proton. So that's another thing is we'll call this a proton when we refer to H plus, because it is literally a proton. You've taken hydrogen, which typically has one electron kind of floating around on the outside and one proton in the middle, and we've just gotten rid of the electron. So it is literally a proton kind of floating around. But that proton will get shuttled around between these things. So it's this dynamic thing that's happening. The proton will be on that one, and then it'll just kind of get handed off to this one. And then it's here. Right, so the protons just kind of get shuttled around inside of the solvent molecule. And that's why we write it as H3O plus. Okay, because if you were to kind of like take a snapshot of the solution at any point in time, you would never see just like an H plus just kind of sitting by itself. It would always be bound to some solvent molecule. So it's just kind of rapidly interchanging between all the different solvent molecules in the water. And so that's sort of your visualization of what's going on microscopically when I add acid to water, and I'm talking about pH and stuff. Okay. So usually when we talk about H plus, we don't talk about H plus concentrations. We talk about pH. So if I have, let's say I have a solution that is 0.1 molar of H plus. So that's my H plus concentration. So you'll notice here I'm using H plus and not H3O plus, just because it's easier to write. And I want to calculate the pH of that. All I do is take the negative log of the concentration of H plus, which in this case is 0.1. And so I get a pH of 1. So remember, for pH, lower pH is more acidic. So the lower my pH is, the more acidic something is. So pH of 1 is, log base 10. A pH of 1 is super acidic, right? 7 is neutral. And above 7 is basic. What can we say? So I guess one thing to point out is like the pH is just the log, since we're just dealing with a log here, or the negative log. Your graph for this is going to look something like if you were to take the log x, negative log x, or negative log, let's say H plus. So if you plotted pH as a function of H plus concentration, this is where H plus equals 1. You can totally have a negative pH, right? So once you get to your concentration where you're like, let's say you have a concentration of 0. Let me think about that. Sorry. It's the opposite. So once you get to a concentration that's above 1, it's like, let's say you have a 1.5 molar equal to H plus. If we take the negative log of that number, I end up with negative 0.18. And there's nothing wrong with that, right? So like normally when we talk about concentrations, we're not talking about their logarithm. So it would be weird to have a negative concentration of something because that doesn't really have any kind of physical meaning. Like it's like you can't have negative. It's like if you made a glass of Kool-Aid or something, right? You can't like dissolve negative amounts of Kool-Aid into the water. That just doesn't make any sense. But because we're just applying this mathematical function to it and transforming it, having a negative number isn't anything special. It's just, that just means you have a proton concentration that's greater than 1. And so as you get above 1, you start to see these negative pHs, and that's fine. You can have a negative pH. So don't let that trip you up. That just has to do with this transform here. So why the hell, I guess one question that would come up is like, why do we use, instead of just, since all we're really concerned about, right, ultimately when we're talking about acids and bases, typically what we're concerned about is the H plus concentration. Why not just talk about proton concentration? Like, why not just leave it as this? Why do we even take the pH at all? And the reason is that at 0.1 molar, it's not really a big deal, but sometimes you're dealing with H plus, sometimes we'll be dealing with H plus concentrations where they're very small. So for example, in pure water, where we're talking about H plus being equal to 1 times 10 to the minus 7th, now you're getting into some like pretty weird numbers there, that are harder to kind of work with. So by taking this and applying it, this log to it, now I get these nice numbers to work with. So instead of having to say 1 times 10 to the minus 7th, now I can say pH of 7. And because because the acid-base chemistry is so like, is used, I guess, in so many places, it's much easier to talk about in whole numbers. So if I say, the pH of something is 3, it's much easier to recognize that that is acidic than if I say like, oh, the proton concentration is 1 times 10 to the minus 3rd. So it's just a matter of convenience of numbers. It takes things and transforms them from these weird kind of long decimals to these nice, whole numbers, or whole numbers, sorry, not the right word there, but things that are more like integers, 7, 8, that kind of stuff. So that's the only reason that we use log. But ultimately, what we're working at is this. We haven't really done anything by doing the logarithm. It's just a mathematical operation to make the numbers easier to work with. Okay. So we have pH that's equal to the negative log of the proton concentration. We can also talk about the OH minus concentration. So this is where things start to get a little bit interesting. Like, so OH, because we're in water, and that's primarily the solvent we're working with, we have this equilibrium here. So remember, when I'm referring to this, a lot of times I'm just writing it as this. It's the same thing. You can just think of it as shorthand for H3O plus. But because we have this equilibrium here, these are both liquid. They don't show up in our equilibrium expression. So we know that Kw is going to be equal to OH minus times H plus. I'll write it out full here, H3O plus, again, same thing. And that's been measured a million different times. And we know that the exact Kw is 1 times 10 to the minus 14th. What this equilibrium tells us, though, is that if we know H3O plus, or it sort of tells us that it just tells us that H3O plus and OH minus, I think I said this last class, they're sort of tied together in the sense that they are, they're tied together through the equilibrium constant. And you can think of them as just being opposites of one another. just in the example I used was hot and cold. If something is very hot, it's necessarily not cold. And if something is very cold, it's necessarily not hot. These are diametrically opposed things that can't exist simultaneously. I can't take a hot and cold shower simultaneously. In acid-base chemistry, it's the same thing. You can't have a lot of acid and a lot of base in solution. It just doesn't work that way. These two things are opposed. They'll come to equilibrium and you'll have either a whole bunch of one, a whole bunch of other, or it'll just be a neutral solution, but you won't have both existing simultaneously. So strong acid and strong base don't exist simultaneously in solution, at least not in large concentrations. So what we can do though here is we can say there's two different ways of expressing sort of the same thing about a solution. So if I say the pH of something is, or let's go back to that example we talked about at the top. If I say that H plus is equal to, no, hold on one second. So if this is neutral, so when it's neutral, is at pH of 7. Or another way of saying that is when the H plus concentration, H3O plus, is equal to 1 times 10 to the minus 7th. Which means that OH minus must also be equal to 1 times 10 to the minus 7th. So in a perfectly neutral, like if you go and buy, I don't know about distilled water from the grocery store, but if you have like really, really pure water in a lab, let's say that you're working in, and it's perfectly neutral, the pH will be exactly 7, and the proton concentration and the hydroxide concentration will be exactly equal. Water that comes out of the tap is typically not going to be perfectly neutral. I forget if it's acidic or basic in Austin, but water that's been left out, water that you buy is probably typically a little bit acidic. But if I deviate from that at all, so let's say I look at the example where if I increase H plus, then OH minus must decrease. And that corollary of that, which I'm not going to write out, also holds, which is that if I increase OH minus, H plus must decrease. And that falls out of what is essentially this equality that must hold, right? Kw is always going to be 1 times 10 to the minus 14th. So if I increase the concentration of H3O plus, the only way that this statement here can hold true is if OH minus goes down. So if I look at the situation where H plus is equal to 0.1 molar, I can say, well, what is OH minus, right? So a question, like a beginner question for acid-base chemistry could say, what is the concentration of OH minus in a 0.1 molar solution of H3O plus? Okay, so that could be a starter question. And so what you would say is like, so we don't have, we've got this like what's the concentration of OH minus, and it's a 0.1 molar solution of H3O plus. How do we figure this out? So usually when we're asking you to calculate the concentration, like if we were to say like, what's the molarity of a solution of such and such, we give you some amount, like it might be phrased like, what is the concentration of a solution made with 5 grams of such and such, right? That's typically how you would calculate the concentration of something. But because in acid-base chemistry, especially at least in water, these two things are tied together through Kw, you can calculate one if you have the other. So I know that H plus times OH minus, at least at room temperature, should equal kW, which is 1 times 10 to the minus 14th. And so if I know H plus is 0.1 molar, then I have an equation where I have one unknown, and I can just solve for that, right? So OH minus then is just going to be equal to kW, which is 1 times 10 to the minus 14th, divided by 0.1. Let me get this, that makes mathematical sense. So yeah, so what's your OH minus concentration? It's 1 times 10 to the minus 13. We've got a question about an antilog here. I'm going to get to that in like 1 second. So right now we're not working with pH at all, right? So pH and pOH are related but not identical to the concentration of H plus and OH minus. So you got to be careful when you're dealing with these problems about what it's asking for. So here it's saying, what is the concentration of OH minus in a 0.1 molar solution of H3O plus? There's two ways that we express concentration here. One is the way that we're super familiar with, which is we just write out 0.1 molar or whatever. And that's kind of what we're representing here. pH and pOH are different ways of expressing concentration. But let's take a look at our result here and think about it, whether it makes sense. So this is 1 times 10 to the minus 13th. If we want to compare it directly to our H plus concentration, that's going to be equal to 1 times 10 to the minus 1. I know that these, we'll do acid in red and base in green. Does this make sense? So remember what I said, that if you have a lot of acid, around, you cannot have a lot of base around. And so if we write these numbers out to where they actually look like numbers and not just like whatever the hell scientific notation looks like, we've got 0.1 for the H plus concentration. And then for OH minus, we've got 0.0000000000000 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 molar of that, right? So this kind of demonstrates what I'm saying, is that if you have a lot of H plus around, we cannot have a lot of OH minus around. So if you think of 1 times 10 to the minus 7th as being the set point, since we know that neutral is 1 times 10 to the minus 7th, and that's equal to the H plus, which is equal to the OH minus concentration. As I deviate from this number, 1 times 10 to the minus 7th, I expect that the difference between the concentration of H plus and OH minus should get larger and larger. So as my H plus concentration goes up, which is exactly what we're seeing here, right? It's going from 0.0000001 to 0.1. What I'm going to expect to happen is that this is going to have to go down proportionately so that this kW expression can hold. Practically speaking, all I'm saying is that if you know H plus, then you can calculate OH minus through this expression. So if I know one, I know the other. That's really all I'm saying. And I'm trying to get you to think a little bit beyond that and saying that you expect that as one goes up, the other goes down. You won't have a whole lot. There's no way to have, and when I say go up and go down, I'm saying going up and going down from their sort of set point over here of 1 times 10 to the minus 7. As they deviate, as one deviates from that, if the concentration goes up, then we expect the concentration of the other one to go down. So that equilibrium constant is it's a sort of our set point for our acid-base chemistry. So someone asked about logs and anti-logs. That is a good question. So then pH and POH. So another way that we could phrase this question would be, what is the concentration of OH minus in a solution with a pH that's equal to we did this up here. I should be able to do that simple math in my head, but it's early and I'm tired. With a pH equal to 1. So now the problem has changed slightly. It's the same situation. Yeah, all it's saying is, so pH and POH are really the same thing as saying OH and H plus, right? It's not that different from saying this and this. All we've done is just a simple mathematical transformation to it, and we just have to be careful that we back that out to make sure that we're it's just translating it back and forth between kind of two different languages. You know, OH minus and H plus in terms of molarity is one language, and then pH is a different language. It's just a different scale. It's kind of like going between Fahrenheit and Celsius. They mean the same thing, right? But you just need to make sure that you're kind of talking about the same thing when you talk to somebody else. So, you know, if I say it's 32 degrees outside, if that's in Fahrenheit, that's pretty goddamn cold. But in Celsius, right, that's like a pretty warm, I don't know, pleasant day. It's been a while since I've been in a place where they use Celsius all the time. I think 32 is a pretty nice day in Celsius. 40 is when it starts to get kind of like, that's more Texas weather in the summer. But anyway, so what's the concentration of OH minus in a solution with pH equal to 1? So one way we can work this problem is to say, well, I know that the pH is equal to the negative log of H plus, and as Frida pointed out, we take the anti-log of that concentration. So if I know that the pH is equal to 1, well, I can write out the equation for it. So H plus would be equal to the anti-log, which is 10 to the negative pH. Okay, so all I did was take this negative, I move it over here to put it in front of this, and then I raise that to the power of 10 because it's log base 10. We're almost always working in log base 10 or using natural log in this class. But so H plus is equal to that. So then I know that H plus is just going to be equal to 10 to the negative 1, which is exactly what we knew already from the last problem, which worked, which is that this is just 0.1 molar. So all I did there was change it out of scientific notation. No, nothing really fancy. Wait, 10 to the minus 1. Did I mess up somewhere? No, I'm good. Yeah, 10 to the minus 1. It's like, I guess it's 1 times 10 to the minus 1, really. That's what it ends up working out like. No, I'm good. 10 to the minus 1. It's 1 over 10. Okay. All right, but yeah, so now we've got H plus is equal to that, and then the calculation becomes the same, right? Okay, so I know that H plus times OH minus must equal 1 times 10 to the minus 14th, and I can take this value and plug it in here and solve. Another thing you can do, though, you could do, I can show you the derivation, it's not particularly complicated. If I take H plus times OH minus equals 1 times 10 to the minus 14th, and I just take the negative log of everything, this maps this equation. So remember what I was saying about how like it's just like going between Fahrenheit and Celsius. This just takes this equation and puts it in the language of pH. So negative log of H plus H minus means that you end up with, just because of the weirdness of how logarithms work, this is the same way of saying, this is one of the nice things, I guess, about logs. This is the same thing as saying negative log of H plus negative log of OH minus is equal to negative log of 1 times 10 to the minus 14th. So this is our definition of pH. This is our definition of POH. And this is just something we shove into our calculator to get the number 14 out. So we end up with this other expression, which is just that the pH plus the POH equals 14. I think they would both be negative. Oh yeah, sorry. Is it true? Yeah, plus, yeah, in my mind, it's like plus the negative log. Yeah. Thank you. So this is just another way of getting at it. So if you know this equation, this makes this problem easier because I can say, well, if I know the pH is 1 and I want to know what the OH concentration is, or I guess I don't know how much easier it makes it, but you can say if the pH is 1, then I know I can do the math in my head now. This sort of shows you why we work in the pH scale. That means that the POH is equal to the 14. It's going to be 14 minus the pH, which is going to be 14 minus 1, which is going to be 13. And then if I want to take POH and map it back to OH concentration, then I would just take the anti-log of that, which would be 10 to the negative POH. It's going to be equal to the OH concentration. And so it'd be 10 to the minus 13 is equal to OH, which is the exact same result that we came out with before. So nested together, we have a series of equations that allow us to kind of jump around here. So this is sort of like the grammar and that we use in acid-base chemistry. So pH is equal to negative log of the proton concentration. H plus is equal to 10 to the negative pH. So if your math is weak, which I know is just from working with students individually, some of you guys that's going to be true for. Start practicing your algebra type stuff. You can reach out to me if you need some additional resources. You don't have to be some sort of grandmaster of logarithms, but you should not be. The goal here is not to be memorizing this equation and memorizing this equation. You should be able to jump back and forth between those pretty easily. And it just depends on what your education was like in high school, as far as how good you're going to be at that stuff. It's not really that much to do with you. So we have these relationships, and then we also have this relationship. And this equation relationship, pH is equal to 14. So you should be comfortable being able to kind of jump around between concentrations of OH minus, H plus, etc. Using these or pH, POH, etc. using these equations. If you're struggling with that in some way, hang out in office hours. Well, I mean, you probably haven't worked that many problems, but if this is kind of like overwhelming or something, hang out in office hours and we can work some problems. Okay. So, from here, we start actually talking a little bit about chemistry. We have a divide in how we can talk about things. We have strong acids and strong bases. And we also have weak acids and weak bases. We're going to start out just looking at strong acids and strong bases. Let's see. So if you go to, let me grab it right out of the website. If you go to, I just posted it in the chat, but if you go to the GChem website, there's a list of strong acids and a list of strong bases. Strong bases are almost always hydroxides. Here, strong acids and strong bases. So strong acids will be things like, I don't want to write them all out, but like the canonical strong acid would be something like HCl, or maybe like nitric acid. Those are examples of strong acids. Strong bases are, what I was trying to say is just like metal salts of hydroxide. So it'll be OH, and then in front of it, you'll have some sort of metal, like a group 1 metal, like sodium hydroxide or potassium hydroxide. If you look in the list, they have some other ones like group 2, like calcium hydroxide, etc. The nice thing about this, though, is that if you know all the strong acids and strong bases, then everything else that's not on that list, you can consider a weak acid or a weak base. But let's talk a little bit about what we even mean when we say strong bases. So there's some confusion, I think, that you'll see if you start reading about strong acids and strong bases. Strong doesn't necessarily mean reactive. I mean, it typically also means reactive, but that's not what it's referring to. Strong is referring actually to the equilibrium concentration. So, you know, like for example, like well, we'll get into this in more detail because we're running out of time. But so HCl, let's say, this is what we'll pick up next time. So HCl, let me look at the Ka real quick. Yeah, so HCl is in equilibrium with H plus and Cl minus. So this is in water. Here, let's just leave it that way. The K for this reaction, the equilibrium constant, is 1.3 times 10 to the 6th. Okay, so what you could do is you could say, let's say that your initial concentration, if you want to work on this, if your initial concentration of HCl is 0.1 molar, what is the concentration of all species at equilibrium? So we just had an exam on this. So so what you can do before Friday is write out a rice table and see if you can solve this problem. How much HCl is actually left over? And this kind of gets at the core of what we mean when we talk about a strong acid. What you should find out is that you don't have very much HCl at all. And this is exactly what we would expect just from what we know about equilibrium constants. The larger these things are, the greater they are than 1, right? The more they are product favored. So at equilibrium, if the K value is equal to 1, that would mean that we would have 50% H plus and Cl minus and 50% HCl at equilibrium. Once it gets above 1, then you start to have a lot more product than you do reactant. Here, our K value, just to spell it out, is 1,300,000, right? So that's a much larger, if you have $1 versus a million, $1.3 million, right? That's a very different amount of money to have in your bank account. And so in this case, that difference in number just tells you that it's going to be heavily product favor. But go ahead and do this calculation, because we're going to be doing a shitload of these calculations for this chapter, and see what you come up with. And then when we pick up on class on Friday, we will start to get into what starts to be really challenging for students, which is, or sort of the edge of what starts to be challenging for students. We're going to start working with weak acids and weak bases, where the equilibrium constants are not large. And then we have some Rice tables that we have to deal with that. And then things start to get really ugly for people, I think, when we get into buffers. But I'm gonna guide you. HCl, that's a good question. Yeah, HCl will be a gas. I guess that makes this calculation kind of complicated. And how do you... I will guide you to the promised land. I'm trying to think if you can just treat it as being aqueous, just so you can kind of get at the right answer, because it's like, well, if it starts out at 1 molar, see where you end up with. See where you end up with keeping it as a gas. I'll be honest, I've never actually worked through what the concentration would be, just because I know it from working with it a bunch of times that it comes out to be equal. So I don't know. Give it a shot, and let's pick up on Friday. And if it ends up being kind of a boondoggle, I don't know. I'll hang out in office hours and work on it. But yeah, let's see. Let's pick up here on Friday, and we'll move into weak acids and weak bases. Let's see how you do on this. And let me take a 5-minute break and drink some water, and we'll take a look at this stuff. We won't do any new material in office hours. We'll just work on this type of stuff. So, all right.
Would office hours be a good time to ask about the difficult test questions, or should we ask Ryan that, or ask him later? That way we can go questions we missed. We can learn them for the final exam.
Yeah, that's a good question, Taylor. Yeah, so we can work on test questions. I worked on test questions on Monday in office hours. So some of that is up. I would prefer, I think, today to work on acid-base stuff, but if you can ask them to Ryan. But if we have time and no one has any questions, we can work on them. So, but office hours are kind of a free-for-all. You can ask whatever you want in there.
Okay.
Yeah. All right. I'll see you guys in a little bit. So yeah, so I guess the answer is, yeah, maybe we'll get to those in office hours today if there aren't a lot of people in there. It's not a bad time to ask. But if we don't, then Ryan is a good resource for that for sure. Recordings are on YouTube. I think I just started uploading them. The ones for Unit 1 are on there. Yeah, Daniel, that's what you should end up with. 0 molar HCl and 0.1 molar for both H and Cl. Yep. All right. See you guys in a second. All right. What do we got?
Dr. Dragnet, could you go ahead and scroll up? I missed a couple notes on the page above.
Up here?
Yes.
Are we good? I got a question from Christine, which is whether we haven't been over this. I don't think we've been over this just yet. Which is whether or not, let's see. Question is, does KW, KP, it's not, no, it's okay. It's not the same as, it's related to, so the question is, we're kind of getting ahead, but the KW equals KA times KB, is that related or is it the same as this? And the answer is that they're related, but they're not identical. So yeah, how deep do we want to get into this? So I guess the answer is no. So I would say if you look at the definition for Ka, let's say you have HA back and forth between HA plus and A minus, and then we look at B I guess this would be BH plus there. So here B is just like a, well, actually, we just start by calling this B minus. Not that it really matters. But so HA is some generic acid, and you need to find the concentration of H plus when given the Ka. Yeah, if you're given the Ka, oh, I see your question. Yeah, if you're given the Ka, you have to go through and find the concentration of H plus. So Ka is going to be equal to this whole thing, and Kb is going to be equal to I got my thing wrong up there. This whole thing. And so there's a way to go between, to show that this, there's a way to derive this from this, but they're not the same thing. Yeah. Yeah. The relationship is similar though, like the kind of what we were saying in class today about how like if H plus is really big, then OH minus has to be really small. The same thing is true over here. Ka, if it's really big, that means Kb is really small. Yeah, I guess really if I want to be, yeah, if actually probably the right way to write this out, because Ka and Kb have to be tied together through the same thing. It should be written like this. And we'll get into that more in class. So it gets confusing, but they're all sort of tied together. That's the way to do it. Now they're related. But yeah, they're not exactly the same. Yeah. So the stuff, I wish we'd have gotten a little bit further today because it'd been, we'd have more to talk about in office hours. I don't want to get into Ka and Kb too much because I want to save that for class, but we can talk a little bit about equilibria and such. Do you guys have any specific questions? So the starting point for this stuff is to get really good at this. And I'll see if I can make some problems for that. I don't know if I have time to make the solutions for it, but I can at least write out some problems for that to post for the homework. But you want to work like 10, 15 of those problems until it's like, okay, I get it. This is pretty boring. Even if it makes sense, you just to get the feel for it, make sure you're putting in the logarithms in your calculator correctly, all that kind of good stuff. And then you sort of have some like basic language to where we can move on to some of the more complicated stuff. Or I don't even say that. You sort of have some of the basic language necessary to just like not miss problems on an exam for something silly like not remembering to take the negative log or something. I don't know. It's just sort of a lot of stuff, I think, to keep track of. But if we look at sort of this problem that I posted just now, which is just to say that, if I've got HCl, and I'm dissolving it in water, so if I want to be a little bit more technically correct, I can write this out this way. So liquid and the gas don't go into the K. And we said this was the value of K for this at room temperature. So hydrochloric acid is a strong acid. It's like, it's the canonical, meaning like, the go-to one that everybody thinks about. A strong acid for not just general chemistry, but just chemists in general. It's like, well, get some HCl out, or that, or sulfuric acid maybe. But the K value is equal to 1.3 times 10 to the 6. So if I have like, I forget what I gave you in class, but I have a 1 molar solution of this, I can say, well, what's going to be the concentrations? So if I start out with 1 molar of this, so if I have 1 molar HCl and dissolve it in H2O, what's the concentration of all species? I could write out a K value here. We'll see that this is actually a little bit more, it's a straightforward problem to solve, but this sort of teaches you the behind the scenes stuff of why things work this way. We could say that the K value is going to be equal to this. And then you could put together a Rice table here. So this is our initial, or this is our reaction, initial, change, equilibrium. This doesn't even enter into the equation because it's water. We start out with 1 of this, 0 of this, 0 of this, minus x, plus x, plus x. And then we can write out our equilibrium concentrations. See, I don't know, because it's a gas, so this ends up working out. Maybe we'll have to treat that as something. Oh no, because it's a gas. Sorry, if it's a gas, we can enter it in. Yeah, if it's a gas, we can enter it in. If it's a liquid, it doesn't go in. Okay, we're good. But so we can solve this. Sorry, I should include HCl down here. Sorry, so remember for equilibria, if it's a solid or a liquid, it doesn't enter into the equilibrium expression. But if it's a gas, we can still put that in. But so we end up with K is equal to H3O plus Cl minus divided by HCl. And we can plug in all these values that we came up with. So you remember we set the H3O plus concentration to X. We set the Cl minus concentration to X. And we set our HCl concentration to 1 minus X. And so we go ahead and we plug that all in. We say we got X times X divided by 1 minus X. And we know our equilibrium concentration is 1 point, because we were given this, equal to 1.3 times 10 to the 6. And so we can solve this. So there's a couple of ways to solve this one. You can multiply this out and get a quadratic equation out of it. So, if I take and try to, I don't know how good your quadratic solving skills are, but you could say, like x squared is equal to 1.3 times 10 to the minus 6 times 1 minus x. And then you could distribute that and say 1.3 times 10 to the minus 6 minus 1.3 times 10 to the minus 6 x. And then we could subtract out x squared from both sides and say, well, 0 is going to be equal to negative x squared plus 1.3 times 10 to the minus 6. Yeah, sorry, 10 to the 6, not 10 to the minus 6. Thank you. Plus minus 1.3 times 10 to the minus 6x. And now you've got something that's more or less in the quadratic. You'd want to put this in the middle, maybe. I'll rewrite it just to be super explicit. So you end up with this quadratic equation. So we could put that into plus or minus square root of b squared minus, God, it's been so long since I've used this, 4ac over 2a. Is that what the quadratic is? So x is equal to that. Yeah, okay, good. For a second, I was like, I don't know. This math skills really atrophy over time. All right, and then we could plug in, so A would be equal to -1, B would be equal to -1.3 times 10 to the 6, and C would be equal to 1.3 times 10 to the 6. And you could plug that all in. And you would end up with two values because, x squared is a parabola. So it ends up crossing through twice. One of those values is going to be nonsense. It'll be a negative number. I guess really because it's negative, it'll be flipped upside down. But one of those will be nonsense. It'll be a negative number, and one of those will be a positive number, and that's the real number. Or so that's the brute force way to kind of get the problem. Whatever x ends up equaling there would end up equaling your H3 or plus concentration, and you could kind of use that for all the different values. But typically, if, let's see, let me think about that for a second. Yeah, actually, I think you have to use the quadratic. All right, so I am not going to work through that by hand because I don't want to. I'm going to find a quadratic solver online.
X works out to 0.9 repeating basically.
Okay, cool, thanks. Man, I really don't want to have to solve this same thing. All right, so so x equals 0.9. Or maybe the right way to write that out is this. And so what we see is x is approximately 1. And so all this is really meant to demonstrate. I'll write this out just to make it more obvious. So all this problem is meant to demonstrate, though, is that for large values, and this is extremely large because it's 1,000,000, for large values of k, it's as if the reaction isn't at equilibrium at all. It's as if it just goes to completion. So if we go back in and plug in our values here, so remember, HCl was equal to 1 minus x, H3O plus was equal to x, and Cl minus was also equal to x. What's our concentration going to be? It's going to be 1 minus 1. So this is going to be 0, this is going to be 1, and this is going to be 1. So, we went through this sort of quasi-laborious process of writing out a Rice table, et cetera, et cetera. So the lesson here, though, is that for strong acids, basically things with extremely large equilibrium constants, and for you guys, this is just anything that's listed on that GenChem link that I gave you that are strong acids. All of those have equilibrium constants that are so large that you don't have to go through the process of this process of solving a Rice table. You can just assume that the reaction goes entirely to completion. So instead of going through all of this trouble, you could say, okay, so I've got this. So if the question is, what is the pH of a 1 molar solution of HCl, even if they give you the K value, you don't have to work it that way. You just assume that the reaction goes to completion. So if you think back to how we solve problems, initially, if you think back to how we solve problems, like before we thought about equilibrium, you solve this in the same way. So it's like you forget about the stuff that we learned about equilibrium, and we say, okay, well, if this is my reaction, and I start with 1 molar of this, I can just look at the molar ratios here and say, well, I know that at the end of the reaction, I'm going to have 1 molar HCl and 1 molar chloride. It's the same thing as saying, like when we looked at things like if you take sodium chloride and I have a solid and I dissolve this in solution, how much, let's say I start out with 1 molar of this initial or whatever. What are my final concentrations of all these things going to be? Well, it's going to be 0 molar in sodium chloride. It's going to be 1 molar in this. and 1 molar in that. Right. So this may be confusing. I don't know, because it's been a long time since I've had to learn this. But I'll say from working with students individually on these types of problems, sort of the like blurry understanding I think that students will get of how, pH equal to 0. Good. So your pH here would be equal to the negative log of 1, which is right where, if you look at negative log x, it's right here. So that's where it equals 0. But yeah, I think sometimes what happens for students is like the understanding of how stoichiometry works can be a little bit blurry, but you can still solve problems, which is what, the way the system is kind of set up, is to just take exams and push through problems. And this is the point at which that can catch up and start to be a little bit of a painful thing. So, I've had students, and there's nothing to be embarrassed about, but I'll have students come in and say like, if I'm starting with 1 molar of this, how do I end up with 1 molar of this and this? Like, you expected this to be 0.5 molar and this to be 0.5 molar. It's like, this is breaking up in half. And it's not a unreasonable way to think about things. It's just not how chemistry works. These are ratios of one another, right? Like 1 to 1 to 1. Whatever, one of these forms one of these and one of these. Just like if you, I'm trying to think of an equivalent for that. Yeah, it's just like if you start with like 1 hamburger and you break it up into buns in the patty, you start with 1 hamburger, but you end up with 2 buns in 1 patty. Those numbers they're ratios of one another. All right, so if I have 1 hamburger, I'll draw it out again. So here's my hamburger. And I think part of the reason this stuff gets, so now I've broken it up. Now I've got my 2 buns and patty. Let's just erase that. We'll say 2, 1, 1. I think the reason, I think the reason that this gets confusing is just because like this feels really abstract. Like, what the hell? No one has experience with microscopically what's going on with sodium chloride. There's nothing for your brain to attach to that makes sense visually. Whereas if you think about it here, it's like, okay, like I've got 1 hamburger, I end up with 2 buns and 1 patty. Like there, it's like, oh, okay, obviously these numbers over here don't have to sum up to 1, right? And that's what's happening up here. It's the same thing. It's like my recipe for making sodium chloride or whatever involves 1 sodium and 1 chloride, and I'm just sort of going in reverse and pulling that apart. Yeah. So don't let that kind of basic stuff trip you up, or if it is tripping you up, don't be embarrassed to ask about it during office hours to me or Ryan. If anybody gives you a hard time about it, I don't know, screw them. This stuff's reasonably difficult to get a handle on. So, but yeah, so for strong acids and bases, you just treat it as if it's a normal stoichiometry problem where it's like, okay, if I have the limiting reagent type problem stuff that we learn initially, which is like whatever I start with tells me exactly how much I end up with, and I don't have to worry about the K value. Oh yeah, so the pH of a 1 molar solution. So what is the pH of a 1 molar solution? Sorry. So in my mind, I finished it, but I didn't exactly. Perfect. Yeah, so the pH just ends up being the negative log of 1. So basically, if you're given, basically for strong acids, whatever this concentration is that you're given ends up being the concentration of H plus in solution. So like I start out with 1 molar of HCl and I end up with 1 molar H plus. And so, you know, this is the same as saying, what is the pH of a 1 molar solution of H plus is essentially the deal. So pH is equal to negative log of 1, so pH ends up equaling 0. It might feel weird that pH is equal to 0. It's just because we're working in logarithms. That's all it is. Your concentration of acid is actually really strong, or really high, I guess. 1 molar solution of HCl it'll make it. It doesn't. It's not as like dramatic as like in movies where you see like acid fall on somebody and it's like there everything melts. But if you get 1 molar HCl on you, it'll itch and make your skin red. And if you don't rinse it off, it'll get pretty irritated. If you dunk your hand in the HCl and maybe leave it there for an hour, then you'll be in trouble. Not that I'm saying you should be careless with acids. They just don't work exactly like you want them to, or you might expect them to. Some of them are pretty nasty, and that HCl is not one of them. Okay, yeah. Can you do the exact same problem but with a strong base? So for strong base, we could say like, and let's make the problem a little bit more complicated. We could say, what is the pH of a 0.1 molar? Let me work with a number that's not perfectly, let's say 0.35 molar solution of sodium hydroxide. Okay, so important here to note that we're asking about pH, but we have a base down here. So how do we recognize bases? Generally, bases are salts of hydroxide, sodium hydroxide. So the general formula would be something like M plus and then OH minus. It's important to remember, it's important, although I think it's difficult sometimes for students to remember, and I should have pointed this out with the HCl problem. This is really the base. This part of the molecule or the compound or whatever doesn't really do anything. It's a spectator ion. And if we go back up here to HCl, it's the same situation. The acid is this. This is just a spectator. Like, yes, you form a bunch of chloride over here, but what effect does the chloride have on the pH? None. Doesn't factor in at all. And so for acids and bases, particularly, especially, I guess I should say, for strong acids and bases, there's always this like other thing that's lying around that doesn't really matter that much. So if we look at sodium hydroxide, you know, so if you want to just solve the problem, you can just start by kind of like plugging numbers into pH. Like I'm sure if you can find videos of people working these problems where it's like, well, I know this, oops. You just see people immediately just start going to the formulas, and that's fine, I guess. I don't know. I wouldn't recommend that. It's a chemistry course. It's like always smart, I think, to start out by writing the chemical reaction. So I write out my chemical reaction here because we definitely, but when we get to like the titrations and stuff, you don't have a choice in writing out the chemical reaction. So get started on that now, and sort of indemnify or protect yourself of that. Kind of being confused when we get to that point. So that's our chemical reaction. And so let's just call this start of the reaction. We have 0.35 molar of this, obviously 0 of this and 0 of this. And at the end, we have 0 of this, and we have 0.35 molar this and 0.35 molar this. And how do I know that? It's because the stoichiometry dictates that. For every one of these that I have, I end up with one of those and one of those. So I've just taken that sandwich and pulled it apart. And the sandwich is composed of one sodium ion and one hydroxide ion. Yeah, so then what's my pH here? Well, I can calculate the P. There's a couple of different ways to work this problem, but I can calculate my POH by just taking the negative log of 0.35. So my pH is 0.45. And so I can then use this equation that the POH plus the pH is equal to 14. And so my pH is going to be equal to 14 minus 0.45. Or really, this is like 5. I don't know. I guess if we want to round it based on the normal rules that people use, this would be 0.6. It doesn't really matter that much for us as chemists. So 14 minus 0.46 gives us a pH of 13.54. And so it's the same relationship holds as it does for H plus and OH, which is that as the POH gets small, which this is confusing, but as the pH goes down, that means that the OH concentration is actually going up. And so our pH gets higher, which means that the H plus concentration is going down. So there's some confusing language there. It's always going to be, all right, let's see. It's always going to be the same molar values in the products as what you see on the reactant side. That is a very good question. So, John's question is, like, if I'm starting with 0.35 molar, is it always just going to end up being 0.35 molar over here? And the answer is, what would my answer be to that? Let me look at my strong acid, strong base. It depends on the coefficients is definitely the right answer. So generally speaking, those concentrations will be the same. But if you look at the strong acid, strong base list, so for most acids, I guess I would say for all strong acids, I don't want you to get too bogged down in these types of rules because they're not. It's just a lot of crap to keep track of. It's better to just kind of understand fundamentally what's going on. But for all strong acids, it's going to be true, both because the second proton is always weak, and we haven't kind of gotten into that. But for bases, like if I have, let's say, barium hydroxide, now it's not exactly the same. So if this problem if we said, what is the pH of a 0.35 molar solution of barium hydroxide, now we see that it changes. So we've got 1 to 1 to 2. And so at the start, it's not like really what you're doing is you're dissolving this in solution. It's like hardly a chemical reaction, but in the beginning, when I dissolve it, I have 0.35 molar of this. And at the end, what do I use up here? Yeah, end. I have 0 of that. And I have 0.35 of this, but this 2 that's out front here, that 2 has to be applied to the 0.35. So it's 2 times 0.35. So yeah, so this ends up being 0.7, and then our POH ends up being 0.15, and so our pH ends up being 14 minus 0.15, which equals yeah, you just multiply it. And it is it's always, I think the closest thing you can kind of get to drawing this stuff to like real world experiences that you've had and that I've had too. It's not like I can actually see on a molecular scale what's going on with barium and hydroxide. I just am more used to it. Is to think about just cooking, right? It's a recipe. Um, this is like we're sort of thinking backwards here, but like this is like I baked a cake, and these are like the components of the cake, like one egg, and then like two, let's say two eggs, and I'll use what else goes in a cake? Like 1 cup of flour, right? It's like the numbers that are out front here um, are just related to like this whole thing over here. So all you've done here is just like, if we're going to use the hamburger analogy, it's like I've got a hamburger that's composed of a patty and 2 buns. When I put it in a solution, right, it's kind of like I broke the hamburger apart. Well, there's my patty and there's my 2 buns. So what's the concentration of buns in solution? Well, it's twice the concentration of hamburgers that I started with. If I started with 1 hamburger. Once I break it apart, my concentration of buns is twice that. I have 2 buns for every 1 hamburger. Yeah. POH is equal to negative log of 0.7. So get super comfortable being able to jump between POH and pH and H plus and OH minus. It's not hard. It's just like, but it's just one of those things. Like you just have to practice it enough to where you don't have to think about it. I think like it's like you gotta get muscle memory for it. Like if you play a sport or something, you practice to the point that you don't have to think at all while you're doing it. Or like it's like typing, for example, right? Like when you're learning how to type, like you don't have to be thinking about where the A and the B and the C key is. Like you want to just be able to kind of like do that, because the more important thing that you're doing is actually writing. And you want to be able to focus on writing and not focus on where the keys are. And that's the same thing with pH and OH minus and all those type of stuff. You need to be able to move back and forth between those so fluidly that it doesn't distract you from sort of this bigger thing. Let me take a look at the problems. Yeah, what I would recommend, what I would have liked to get to today was just solving weak acid, weak base problems. Let me see if that's broken up in a nice way. So definitely find any problems that are like pH, that are strong acid, strong base problems, and be able to work those. That's the initial thing to work on. But if you want to get cracking on the stuff that starts to be a little bit challenging, I would work on weak acid, weak base problems. Let me see how it's broken up in the homework. Maybe on the GChem website, we have some nice stuff. So I would work on those ungraded problems are kind of just like a, like just a blend of just random problems from previous exams. Some of them are probably stuff we won't get to, but it's a good way to kind of just go through and test. But these are the types of things that I would try and get to being able to do. And there's a key for that as well. So that's from the GChem website. Here's the key. And we haven't explicitly gone over like weak acid problems yet, but it is just sort of a very natural extension of equilibria, which we have gone over. So I don't think you should be able to work those. Yeah, it looks like some studious TA. It looks like they wrote out a pretty good thing for them. Let me look at one more thing here. Yeah, this is not a bad. There's some weak acids in there too. Let me look at it real quick. So if you look down, so problem 6, 7. So some of these are neutralizations though. Ah, damn it. Let me think for a second. I'm trying to think of what I want to get to. We might get to that on Friday. We haven't talked about neutralization reactions last yet. So I would say if you're familiar with neutralization problems, just work them all out. But if you're not, problems 1, 2, 6, 10, and 11 are good problems to work through. Yeah, and then I think on Friday, I'll try and we'll work some of the weak acid problems that you'll have done here, and we'll talk a little bit. Let me see what I have in my notes here. We'll talk a little bit about neutralization reactions. First sheet of the second one. I'm sorry, that's from the first sheet. I'll just make an announcement on Canvas. For the second sheet, just work all of those. I guess you're supposed to know how to do that, right? You should be able to write out the chemical formula for potassium formate. Yeah. So the second sheet is like, in my mind, what am I trying to say here? When I look at that sheet, it's really obvious to me what all those different things are because I'm super familiar with it. And it's unclear to me exactly how to teach how to know that. I think you just kind of have to start by memorizing that. All right, does the concentration of H3O pluses increase or decrease once it reaches 1 times 10 to the minus 7th molar? So at a concentration of 1 times 10 to the minus 7th molar, H3O plus will be exactly equal, at least in pure water at room temperature, will be exactly equal to OH minus. I'm not sure how to answer the question. Decrease, I guess increase or decrease it once it reaches 1 times 10 to the minus 7th. From what? Like, what's the starting point in that, Udita? You know what I mean? You know what I mean? Like, I guess I'll put it in this context. Like, if I were to ask you, does the amount of money in your bank account increase or decrease once it reaches $100? I guess I was saying there needs to be a little bit more context. I need a little more context to answer your question. I'm not sure exactly what you're asking. Oh, I don't know. Yeah, no, I'm happy to give the play-by-play. Happy to talk about whatever. Most challenging content, but what problems would you want us to work a lot on? Let me look. It's hard because that giant swath of problems, that's like 100 problems. I'm not familiar with every single problem in there to highlight it. So the GChem site, I guess what I would say is, here's a bunch of good calculations too. We're like a little bit short on stuff that I've taught you. Let me do this because these are good questions that I can just post to the class in general. Once I get out of office hours, I'll post a list of problems to work on before Friday, and then like kind of over the weekend, so you're kind of prepared. So I'll give you the GChem worksheet problems, and then I'll have to look at those 100 problems, but I would just look for problems that are like that in that giant set of 100 for extra practice, if that makes sense. But the GChem ones will give you some, like a little bit more structure. Yeah. Any other questions for you guys? I know some of you guys have to get to class.
So do we assume all these problems are like in normal water?
Normal meaning
Because
like room temperature water or something, or
Well, you mentioned that like these would just be in, I guess, the solvent water and not any other solvent.
oh yeah, just assume we're always in water.
Okay.
Things get a lot more confusing in other solvents, and I don't even know if that's ever covered in a specific class, maybe like an advanced organic chemistry class or something. We're certainly not going to worry about that. So yeah, just assume water. The only time it'll ever be a little bit different is if it's like water at a different temperature. And that in that case, KW would be different, but we would specify that in the problem. Yeah, no worries, Udita.
KW is always a given, correct?
KW is
It's
always
like
one times it's always 1 times 10 to the minus 14th. But remember that equilibrium constants are constant at constant temperature. And so if you change the temperature, KW will start to change.
okay.
But it doesn't change dramatically. So like, for example, there's a problem in one of the worksheets here where it's like at body temperature, KW is different. It's 2.5 times 10 to the minus 14th. So like it's a little bit different, but it's not like it's dramatically different, you know? But you just have to be careful of that. And I think if we're going to give you a problem like that, we're going to spell it out and say, hey, you know, this is what's going on there. It's not like you're going to have to, you're not going to have to notice that. I think we'll try to be really explicit. I don't really care about that much. There is no SI. What's SI? I don't know. There's no plus session for this class, that's for sure. I don't know what SI is. Student instructor, maybe? Supplemental instruction. No, there's no supplemental instruction either. I think maybe because I'm teaching it in the off, like because it's one off, maybe I get in because it's a pandemic. Nobody approached me about doing a plus session or getting a supplemental instructor for the course. So those programs aren't ones that I run or the chemistry department runs. Those are from Tides or some other department. Yeah. We do have, if you do want extra instruction, though, the other TAs for the other course can help you, and their office hours are on Canvas. So, anything else? Yeah, go to those. I mean, the best thing you can do is, I guess my only advice is on kind of going to office hours and stuff is go in like having worked problems and have very like specific questions. I'm not like commenting on your questions in here. I don't remember what your questions were, but that's my general advice to students is, you know, you don't want to be, the less passive you can be inside of the instructional hours, the better. So if you come in really well prepared with like lots of questions where you kind of got stuck, that'll be a lot more beneficial for your time, you know, for time efficiency and stuff. Some students will show, like when I used to when I was a TA, I remember students would show up to like the review sessions and stuff and just like work on other stuff while they were there. And like, you're not going to learn, people don't learn that way, unfortunately. There has to be some active stuff there. All right, bye y'all. I guess I'll cut out a little early and get this stuff uploaded to Canvas so people know what to work on. Yeah, you guys have a nice Thursday, and I'll see everybody in class on Friday.